Hello. Okay. Um, so this equation, we are going to rewrite this equation by changing certain, by renaming certain variables. For example, for the first factor, we will change notation from x1 from x to x1, y to y1. Okay. So let me do that. X to x1 and y to y1. It is the same equation. I'm just writing I delta j x1 y to x2. Y I am changing to x2, delta x2, not y1. Okay. Then in the second factor, the second part, we change z to v. This z, we change it to v. Okay. So then that will be so this is going to be du dv. This z will be v. Okay, so I have written the same equation. The external points here are x1, x2, z is integrated over, and w, x1, x2, and w. Okay. Here also u and v are integrated over, so this y should be x2, and this x should be x1. Okay. So here also the x1, x2, and w are the external points. Other coordinates are integrated over. Now the trick is you multiply both the terms, you convolute it with G2, multiply both the terms with here W is an external point. I have x1 and x2, and then multiply with G G2 connected W x3. And here also G2 connected W x3, and then integrate over W. So then write it slightly better way. This is what we get. Now, earlier in the case of n equal to 2, we saw these two things are precisely inverse of each other. This is the gamma 2, and this is G2. And you know, when you integrate over the W index, W coordinate, then you get I h bar delta function z minus x3. So the left hand side, after doing the W integral, one would have, and also this this quantity, this 3 derivative is basically the connected 3-point function. So this is G x3 connected x1 x2 z times I h bar delta z minus x3 after w integration. Okay. On the right hand side, so I'm taking the second term on the to the right hand side. What I'm getting, what I should get is integral du dv dw g2c x1 u. Then the middle factor, this one is nothing but g2 x2v. So g2c x2 comma v and g2c x3 comma w. It's actually symmetric, so and then this third derivative. At 0. So this integral, for the left hand side, it is just going to make z x3, and I by h bar factor when brought on the right hand side is minus I by h bar, and therefore we get this following result. G connected 3 x1 x2 x3 is equal to minus I over h bar integral du1 du2 du3 gc2 x1 u1 gc2 x2 u2 gc2 x3 u3 times del 3 phi cl gamma cl gamma phi cl del phi cl u1 u2. This is what the result is. But we already know from our previous analysis that is precisely what when connected Green's function is written in this way, then this factor is precisely what gamma 3 is. So this implies that this object is equal to gamma 3 u1 u2 u3. So recalling definition of gamma 3 discussed previously, we conclude that this is the result. Okay. So that is equation 1 for n equal to 3. Okay. Now let me proceed to derive the same result for n equal to 4. Now onward, there is a systematic method up to, because n equal to 3, each time you prove that result for any value of n, you actually take the result from n minus same result, whatever result you get at n minus 1. So for n equal to 3, you are using n equal to 2 result, and you already did that, right? I mean, that is how we applied this operator on the n equal to 2 result. That is how we got n equal to 3. But n equal to 2 result is qualitatively different from n equal to 3 result, because this is, you know, so this for, so this equation should be for n greater than or equal to 3. For n equal to 2, the situation is slightly different. For n equal to 3 onwards, it is the same thing. It's similar. So that's why after getting n equal to 3 result, if I show how to get n equal to 4, then that procedure will just be repeated for higher values of n. And the procedure is similar to what I just described from going from n equal to 2 to n equal to 3. But there is slight modifications because the structure is different. So proof for n equals 4. So what you do is that perform the following steps. Lift equation 1 for n equal to 3 to non-zero j or phi CL. What I mean is that this is the n equal to 3 result, but these results are obtained by setting j equal to 0, phi equal to 0. If we had not set j equal to 0, phi equal to 0, this will be third derivative of z, right? And we will not have this restriction, this condition. So that, and each propagators will be lifted to second derivative of z. That is the form that I'm referring to. Okay. So this is not equation form. So what I'm saying is that, let me give a new name. Let me call it 3. So lift equation 3 to non-zero j phi CL, then differentiate with respect to j x4, then use identity del over I del x equals integral du del to zj. This is what we used in the previous case as well. This is of course true for non-zero value of j and phi CL. This is just definition that are from the so you first apply the chain rule as I discussed earlier before. First apply the chain rule and del j equals to del phi del j times del phi. Del phi del j can be written in terms of this using that equations in Legendre transformation. So true for non-zero j phi CL. Then finally convolute with let me not write down the argument, but exactly what we did in the previous case. Multiply a G2 and integrate. Now let me implement these steps. So step 1, is lifting this equation, equation number 3, to non-zero value of j and phi cl. Basically what it means is that this will become third derivative of z with respect to ij at these 3 points. Similarly, each of these g2 will be replaced by second derivative of z with respect to ij at these 2 points in the argument. Okay, that is how it should look, and one should remove this at 0. So this will be at arbitrary value of phi cl. That's the equation that one wants to start with. So step 1 says that equation number 3, from equation number 3 we get this equation. I'm using slightly cryptic notations because to save space. Minus I over h bar integral du1 du2 du3, then del 2z I del j x1 I del j u1 del 2z I delta j x2 I delta j u2 and del 2z I delta j x3 I delta j u3 times del cube gamma del phi cl u1 u2. Okay, fine. Then the next step, second step, is to take derivative with respect to I, j at x4 on both sides. This is and then set and then differentiate with respect to jx4 I jx4 and then set j or phi cl to 0. So when you first take derivative, it becomes a fourth order derivative, and then set j equal to 0, then it becomes a Green's function, connected Green's function. So I'm going to directly write expressions in terms of the Green's function after setting j equal to 0. So this is going to be connected 4-point Green's function x1 to x4. du1 du2 du3. Then the derivative j derivative will act on all these 4 factors on the first 3 factors. So it will give 4 terms. First 3 terms will be derivative acting on one of these 3 factors, and after setting j equal to 0, that becomes a g3, and the other two remains to be g2. And the fourth term, where all 3 will remain g2, this will become a fourth order derivative, but the first derivative will be with respect to ij, and it is the job of the step 3 to convert that derivative to phi cl derivative. We'll do that in step 3. So let us write down the 4 terms. So the first 3 terms will be This is G3 connected X1, X4, U1, then G2 connected X2, U2, then G2 connected X3, U3 times gamma 3, U1, U2, U3 plus G2 connected X1, U1, G3 connected X2, X4, U2 and finally let's see. This is what we get. Then we now go to step 3 and manipulate each of these 4 terms in different ways. We'll see what picture emerges from it.